again. Okay. Hello and welcome back to Calculus 2 for the last time. Section 10.3, Calculus in polar coordinates. And yes, tonight we'll complete all of the lectures. Tomorrow is the review, and in 2 days, final exam. Yeah, welcome to the class. 2 days. Yeah, it is. Yeah. Those of you interested in taking the final will be in the classroom on Wednesday. The rest of you will be in the classroom next semester for the same class.
I'm going to bring up the time.
No, it's 5:30.
It's 5:30, you're sure? Okay.
Apparently it's 5:30, I don't know.
I will look it up. Is it this
Of course you will.
No, it's not the other thing. Yeah.
S something.
Or
S something.
I'm not
The
sure.
one
It
that's
doesn't
above
tell.
this.
Yeah, the
It's
one
like
above.
S347 or something like that.
349.
349.
We are taking the final in our regular classroom for Wednesday.
Thank
At the time,
I will be with you in a moment.
It's 5:30.
all of you going to Calculus 3, I really think you should dish out extra money and somehow convince her to take Calc 3. Otherwise, you're doomed.
Well, exam schedule.
Calculus in polar coordinates, we are going to deal with two concepts, derivatives and integrals. So let's start with derivatives. If you take any of the shapes we talked about last time, we mainly talked about the flower and so on. So here's your sine 2 theta. Actually, I can just draw a new one. So say that you have r equal sine 2 theta, which would graph something like this. Observe that we still have tangent lines. And this tangent line must have equation y equal mx plus b. So there has to be a way to find this line. You know that this point is going to be xy, but you know that each point is obtained by r theta. So there is the conversion between the two worlds. The only issue that you have is what is the derivative over here that you have to find in order to have the slope. And x and y are not going to be a problem at all, because if you get r theta, you can convert that. So the slope is the issue. And the slope is in the derivative. So we need to know how to find the derivative in polar coordinates. Now that equation is lengthy, and it is much better to memorize or to realize the way to get it rather than to memorize the formula itself. The formula is not impossible to memorize, it's just too busy. It's much busier than negative b plus minus square root of b squared minus 4ac over 2a. All right, so let's see. We know that the slope m is that f prime of a, which we know it's the dy over dx computed at x equals a, right? So that's all notation for the slope. Therefore, I need to find dy dx. But what are you given? You are given the function r as function of theta. So you are looking for dy dx given r equals f of theta. So let's see how we achieve this. I start from dy dx, and I say to myself, well, I can actually write these as dy over d theta divided by dx over d theta. Remember in parametrization, you just added at 1 over t? Well, this one is going to be far more complicated because observe your conversion. How do you get, so what is this equal to? So how do you get dy dt, d theta, sorry, dy d theta? How do you get it? Well, you have to differentiate y in terms of d theta. But y is r sine theta. So you are differentiating r sine theta. I'm just going to say that the whole thing there is the y from conversion. But now remember, and here I'll write it in blood, remember that r is a function of theta, which means that over here you have a product rule that you have to worry about. So what is the derivative dy dx? It's the quotient of product rules. That's the best way to memorize the formula. The derivative dy dx, which is this when you cancel d thetas, is the division, the quotient, not the quotient rule, the quotient, just simple division of product rules. Because the derivative of y in respect to theta is the derivative of dy, and y is r times sine theta, and r is the function of theta. So you have function of theta times sine theta. And for the dx, you will have r times cosine theta, which is again a product rule. So we plug all of this in to get the formula. So dy d theta over dx d theta is equal to the derivative of r times sine theta divided by the derivative r times cosine theta. And now I'm going to write it one more time so that we are not confused. F of theta, whatever it is, times sine theta divided by the derivative of f of theta times cosine theta. All we need to do is to compute this. So what's dy dx equal to? Derivative. Copy the first, derivative of the second, plus copy the second, times derivative of the first. Divided by, same thing. Copy the first, times derivative of the second, plus copy the second, times derivative of the first. Now we really don't want this minus sign to start off, right? So we're going to swap those, and then we're going to follow the same pattern and write the top. So we first simplify the bottom by placing f prime theta cosine theta minus f of x, f of theta. Why am I writing f of x? Oh, I put it.
Above.
That's the problem. Okay, fixed. Sine theta. And now I'm just going to use the same stuff up there. F prime theta sine theta plus f of theta cosine theta. This is your formula for derivative. Is it systematic to memorize? Yep, because look, prime, prime, function, function, plus and minus, sine, cosine, cosine, sine, sine, cosine, cosine, sine. There are ways for you to figure out how to memorize this, but I would 100% of the time use this because it literally takes 6 seconds to derive it rather than memorize it. If needed, to find the tangent line is needed to show velocities and all that kind of stuff. So it is important part. And you will be using this in Calc2, so just do yourself a favor now before you have that huge meal and forget about it. The rest of it is just plug and chug because what is the tangent line at pi over 3 for that flower thingy that we have? Well, pi over 3, that's the theta you will plug in, but you had the sine 2 theta, so that goes for each of these f's, and then you compute. So let's do an entire problem to find the tangent line where we are actually finding the derivative, and then finding the actual line. So here it goes. Polar coordinates are fun. Find the tangent line for r equals sine 2 theta at theta equals pi over 3. Tangent line, y equal mx plus b. I can find point r theta like this, use the conversion to transform that into x and a y, so I have x and a y for my tangent line calculation. I need m. That's when the derivative comes in. So I just want to see if you guys can actually compute this and tell me what the slope is at the end. Exact value. Tonight.
So this is for finding the slope of it.
No, that's the finding the derivative.
Not to find, that is, that was to find the slope of the tangent.
You circled way too much.
Oh, I circled way too much is right. Thank you.
No. There's no need to flip the book. You know what the derivative of sine 2 theta is. Plug whatever you want. You're just mechanically plugging things in. Replace every f and f prime with, guys, this is your f. This is your f theta, right? R equals f theta. That's the, like you say, y equal f of x. Remember y equal f of x? You better remember that after 4 courses. You had that, right? So y equals f of x, r equals f of theta. Same thing, okay? Same thing. So r equals f of theta. So this is your r, this is your r prime, r. Plug them there. In your case, sine 2 theta. Take the derivatives into the theta, and then I'm going to the F1 by any chance. No.
Yeah, I'm trying to make my mind between fuel and iPod. That is. What's one? Cosine? What? Cosine 5. I did something ridiculous. Figured out a lot. That's probably big. That's how I remember contracts when you were like 11. All states defended. Wait, is the final multiple choice?
It is. You have a choice between doing it or not. So it is multiple choice. Like everything else in life.
So screwed.
Why?
Let's keep it multiple choice. And
Still got it.
okay. I'm in that.
Yeah. But why are you dating him? Why am I dating him? Oh, they are on the line, but the tangent line is not going to be there. It's going to be.
Yeah, but
No
I
buts.
wish I had
Look.
my calculator at home.
It's meant.
it doesn't work.
Yeah, it's meant not to be. You will not know that knowledge ever. All right, let's take a look at this problem together. I hope you were able to do this 100% on your own because it's literally plug and pray, right?
I'll keep that in mind.
It is plug and pray. I mean, that you compute it correctly. What is the actual expression?
You said plug and chug.
Plug and chug, or yeah, but plug and
plug
pray.
and play.
Yeah, plug and play.
It's plug and play.
Plug and pray, yeah.
I like plug-in.
Me too.
Plug-in.
It's the only one I actually use. So, first of all, we have to get R value for this, which is f of pi over 3. And you can't get any other, and I will explain for which reason. So we have sine 2 pi over 3, and sine of 2 pi over 3 is? Very good. So it's still positive, it's in the second quadrant, and it's the 60 degrees.
I'm sorry, I'm confused. What? How do you get the sine 2 pi over 3?
Plug in pi over 3.
Oh, do the 2. Oh,
Yep.
okay.
So now our point for the tangent line is root 3 over 2 comma pi over 3, and we convert that into xy because we have to. So x is r cosine theta, which is root 3 over 2 times cosine of pi over 3, which is a half. So hopefully you guys have pi root 3 over 4. And then we convert y, which is r sine theta, which is root 3 over 2 sine pi over 3, which is going to be 3/4.
Yeah, why is there pi and since they want half times that? Shouldn't it just be root 3 over 4?
That's what I said. This one? It's clearly root 3 over 4.
That's a follow.
No, we just switch the screen.
There.
It was for dramatic effect.
Oh, so I'll keep that in mind.
So,
Ow!
yes.
There we go. Jeez.
So now I actually have that xy point is root 3 over 4 and 3/4. So now I have to find m. So m is going to be the derivative computed at pi over 3. Well, we have the formula that we use, which was, I forgot, f prime sine theta. So the derivative of this is, derivative sign is cosine, so 2 cosine, no coughing please, 2 cosine 2 theta times sine theta
Wait, what? That'd be 1/2.
your chain rule, it's derivative. Integral is 1/2. Oh, you have some constant issues there. You have constant issues. So fix the constants. And then we have regular function, which was sine 2 theta times derivative of sine is cosine theta. And we're going to plug in pi over 3 later. Again, the derivative, so 2 cosine 2 theta times cosine theta minus original function sine 2 theta times sine theta. And now we're going to plug in the value, pi over 3. So I have 2 cosine 2 pi over 3 sine, who picked these numbers? Pi over 3 plus sine 2 pi over 3 times cosine pi over 3 divided by 2 cosine 2 pi over 3 cosine pi over 3 minus sine 2 pi over 3 sine pi over 3. So now we need to compute all of this. 2 times cosine of 2 pi over 3 is 1/2. And then we'll have to, okay, fine. Then you have to check the quadrants, but there was no patience with our young Padawan work. It's good, so it's all good. Cosine of pi over 3 is minus sine of 2 pi over 3 is, very good. And then sine pi over 3, awesome. And then 2 times,
Why did 2 times 1 over 2? It's negative 1/2, and then why multiply it by negative 1/2?
no, this is a root 3 over 2. Sine root 3 over 2, cosine root 3 over 2, yep. 2 cosine, and then another 1/2 over here. And then minus the sine is root 3 over 2. And then sine of pi over 3 is root 3 over 2. And on top is a 1/2. It's good? Just going to adjust the line. Can do that much. Now, I have a 2 cancel with 2. 2 cancel with a 1/2 over there. So I have negative root 3 over 2 minus root 3 over 4 divided by negative 1/2 minus root 6 over 4. Multiply by 4. Doesn't matter which one you cancel out. I discriminate. There you go. I really have no other answer to give you.
Is it going to be root 9?
Where? Oh, it's a 3 times 3 is 9. Eh,
Which is actually much easier than root 6.
it is.
Isn't that just 3?
Yeah.
It is. So negative root 3 minus root 3, first of all, we multiply by 2, so it's negative 2 root 3 minus root 3 divided by negative 2 minus 3. Make everyone happy. This is negative 3 root 3 divided by negative 5, from where we see that slope m is 3 root 3 over 5. Is this what at least one person has?
Yeah.
Great. If you have anything else other than this, talk to the group that led the efforts.
Why did the plus on top change to minus? And why?
Oh, that's a good point.
Because it was a quadrant.
But both those are positive.
Yes, they are.
Oh my goodness, that's just going to change everything now, isn't it?
Nah.
Don't jump to the end. Show us the process all the way through. Damn it, Janet. jump to the end.
This is why I don't take exams anymore.
You should just give us a 80 on the final. Just like 80. Why not yourself?
What do you mean give you 8 on the final? I have more respect than that. I'll give you the final, you score more than 8. All right. So now I have x and y, so 3/4.
Wait. That last figure there, the negative square root of 3, shouldn't that be,
It's negative.
so it's, all right, so it's just, shouldn't it be negative? No, it's negative over negative, okay. Square root of 3 over negative.
So we have 3/4 minus 3/20 is b, times 5 over here for common denominator. 15 minus 3 is 12/20. 3/4. No, 3/5. Are we good with 3/5 on b?
Wasn't that 3/4? Oh,
Yeah, it was.
yeah.
So y equals √3/5 x plus 3/5. And there's the tangent line at pi/3. This pi/3 produced a certain r, which produced certain xy point that you must use to compute. If you move that point anywhere else, the tangent line is going to change, the slope is going to change, everything changes. Yes?
It's like a picture of a flower. You chose X value. Why not just call it?
Because I chose theta pi/3. Right? That gives you a particular. A similar question was asked in secrecy earlier. So say that pi/3 is here. This does intersect or touch the function 3 times, but it's not tangent at any of these points. It's tangent right there.
Well, I was thinking like, if your is pi/3, I was kind of treating it like an X value, like it's going through 3 other points in the function.
Well, it does go to 3 points, but still, it's not tangential, right? Sure, but I can find, see, that could be a cool question for final exam, for instance. Find at which thetas we have a common tangent line. So let's say, right, there's a tangent line that does this, it's tangent here and it's tangent there. So what are these two thetas, right? Or like that, right? What are the two thetas that, those are cool. Or even better question is find this intersection point between these two tangent lines which have these properties. You can find all of those things. Or we can just find the tangent line. So
You had to ask.
Those have any applications in finding intersections?
So they are.
That's a strong word. Strong feeling.
Which one?
8.
8?
Yeah.
I'm not liking you very much right now.
The way it goes, if I love you in my heart, if I hate you in my mind, so it doesn't matter. It's the same emotion on different side of the coin.
So am I in your heart or in your mind?
We'll see. We still have to decide. Depends on the final. Yes. This is the actually XY equation.
Wasn't it pointed downward? Shouldn't it have been a negative b since it crosses the y below?
Pi/3 tangent. Pi/3 tangent is not on the first flower order.
Okay. I guess it could be just weird on that one.
Yeah, I just had a random line. It's nowhere near here because this is. We have to see 0, 0. It's going to start here. But then you have to calculate pi over 6 to see when it's going to draw this way first, that way, or that way. I'm not sure. Definitely 0, 0 is going to start here. And 2 pi is going to end here. And at another 4 times, see, it goes around, so start here. It's going to be 5 0, 0 points. There will be 5 thetas that will give you 0, 0. You start here, you go around 2, 3, 4, 5. So there are 5 thetas in 2 pi. You literally divide it by 5. You have 5 thetas which push you back into the origin of the graph. So pi over 2, right? Pi over 3, sorry, pi over 2, pi, 3 pi over 2, 2 pi. Those are only 4, right? You have to figure out what are the actual values that will put you into the origin there. So you have to figure out which way. Now, I actually want to graph this one a little bit by hand, so I'm going to kill this graph. Let's see how we graph the polar coordinates by hand, and maybe take a look at this. Now, this is extremely important for integration portion, but I'll do it now since there are questions. R is f of theta, which is sine 2 theta. We know it's going to make a flower. If there was a cosine 2 theta, it would be still 4-petal flower, except they would be on axes, those petals. So now, what I'm going to do is say, pick those thetas, 0, pi over 6, pi over 4, pi over 3. Ooh, actually I have a 2 there. So I can go pi over 12, pi over 6. Yeah, pi over 12, that's pi over 6. And then pi over 8 will give me pi over 4. And then pi over 3, right? Pi over 6 over here. And then what's next one? Pi over 4 to give me pi over 2. Okay, let's say this is enough. Why am I picking these values? Because pi over 12 times 2 is pi over 6. So if you pick pi over 6, then times 2 is going to be pi over 3, and you're skipping the whole piece of a picture. All right, so 0 plugged in is returns 0. And you know what? I'm going to have r theta here, 0, 0. So that's going to be origin. We start there. Then we have pi over 12. Pi over 12 returns pi over 6. Sine of pi over 6 is 1/2. So I have 1/2 and pi over 12. So if this is pi over 4 and this is pi over 6, then half of that is pi over 12. Let's put 4 units to be number 1. So half. So first point is right there. Pi over 8 gives me pi over 4, root 2 over 2. So I have root 2 over 2 and pi over 8. Pi over 8 is in between these two. Root 2 divided by 2 is about 0.7. So 0.7 right there, let's say. Pi over 6, no coffee. Pi over 6 is going to be pi over 3, that's root 3 over 2. So root 3 over 2 and pi over 6. Root 3 is about 1.7, cut that in half, call it 1.85. Right there. Pi over 4 times 2 is pi over 2. Pi over 2, sine of pi over 2 is 1. So 1 pi over 4. And this is the peak. So I think that you see that from 0 to pi over 4, we got only the half of the pedal. The other half is going to use up from pi over 4 all the way to pi over 2 in the complementary increments of what we had. So I'm going to use purple to draw, right? And then it would go like this to finish it off. So I haven't gotten to pi over 3 yet, but pi over 3 is right here. And when you draw the tangent line, you see that it's going to positive, right? We have the positive tangent line. And look, if I draw a tangent line, this is a terrible picture, but tangent line at pi over 3. And it actually kind of works, because remember that 4 squares were 1? Look, 3/5, right? It kind of works to be 3/5, this value here, for y-intercept. And we have a positive slope, right? So it actually works pretty well. You're able to do these things. You can graph using the middle school method, right, of picking points and computing the other value. You can graph any of these. And if you're not sure how to connect them, you put in more points to refine it, because they can be any type of a graph. Now, this skill is crucial for integration, which is the next part of this lecture. So for derivatives, now you have, first of all, you see how terribly this flower is going to, how terribly it fails the vertical line test for your, is it a function kind of deal from Precalculus, right? It cuts it there 4 times. But its actual equation, look, it's beautiful, right? It's a beautiful equation. So, again, from last class, polar coordinates complement what you have with the Cartesian coordinates. And these beautiful equations are going to look very scary when you convert them to x and y. This is the reason why we did not convert that to x and y and then use the implicit differentiation. Can you do it? Hell yes. And you have to get the same answer. So if you have about 30 minutes to an hour at home, convert that into the x and y, do the implicit differentiation, plug in, convert theta, obviously, you get root 3 over 4. Plug that in, 3/4, and you will get the same root 3 over 5. You must. Or whatever the hell was, the derivative. Root 3 over 5. So it can be done. But this is actually much faster. Tangent lines show what? Instantaneous change, which means you can talk about motion of the particle. Motion of the particle looks like this, say. So this is extremely useful, and you will see a lot of this, obviously, in Calc2. Now we're going to do integration, and it's going to be much more of this angled kind of thing. Integration in polar coordinates. Is stream still alive? Yes. Nope. So you guys are used to, hopefully, integration in Cartesian coordinates, and some of you understood the importance of representative rectangle and you use it to your benefit to every time set the problem correctly. So if you had, I don't know, two functions intersecting and we wanted to know the area between the two curves, you see immediately that you are supposed to use dx for this problem because representative rectangle slides from left to right and the bottom part will always touch x squared, the top part will always touch the linear, right? In certain other cases, you know that you are supposed to use dy. Again, left and right, always touching the different functions. And you know, hopefully, that if you use the wrong one, hell breaks loose quickly. So if you try to use dx on this piece, it kind of looks good for some time because the bottom is touching x squared, y squared, top is touching linear. But what happens as it changes here, right? You see that you can't use dx. So for this particular object, using dx is out of the picture. You must use dy. That's the same picture, by the way. So if you acquire this kind of knowledge with your representative rectangles, you are able like this to spot whether you have to use dx, dy, and then also it slides, in this case, from left to right, so it has to take on all of the values from left and the right, so that's your a and your b. It has to slide from bottom all the way up, so those are your c and d for limits of integration, and so on. If you are very good with this, we are going to upgrade just a tag for your polar coordinates. And whether they're calling a representative slice or representative triangle or something, I call it representative pizza slice because that's what it is. So if I want to find area of the circle, we know that in polar coordinates, area of the circle is pi r squared. And we know that the main variable, right, that r is equal to f of theta. So integral must be d theta because the main variable is theta. That should be common sense. As soon as you have this d theta here, that means that you have to have a function to integrate, which would be your function f of theta. There's going to be some kind of integral from some kind of theta 1 to theta 2, right? This is incomplete, but this is how you build formulas, right? But there is also this fact that if you look at this d theta here, how would d theta look like? It has to branch out of the origin and go like this. This is the reason why I call it representative pizza slice. Representative pizza slice is more restricted than dx dy. Because your dx dy, look at this. This one travels here, travels there, right, goes left and right. And this one, pinned on these two, goes up and down. This one, no bueno. So now, what is the d theta going to do? D theta is going to do this. It's going to go in a circle. So these limits are going to be angles, which representative slides traces. So for my circle, if I want to find the area of the circle, I better integrate my function r d theta between 0 and 2 pi. But then there's also this half that floats around. Now, is that half supposed to, well, actually, there's also a square here, but actually, you know what, let me give you the formula, and then let's do it this way. Instead of building it, it's not an honors class, so let's do this. I'll give you the formula, and then I'll explain the formula rather than deriving it. A equals 1/2 integral alpha to beta, first two letters of Greek alphabet, and then you have your function squared d theta. First of all, I want to know if dimensionally this equation makes sense. And the answer is hell yes. Areas are two-dimensional, and d theta has no dimension to it. Theta is not measured in inches or feet or kilometers or miles. Therefore, there is no dimension brought by this. Two of these. So here is your r squared, and here is your pi. So pi r squared.
Can you do that again?
One more time. We know that r equals f of theta. So this puppy here is r squared, and you're going to get your pi from limits. Because this is angles in radians. So when you are dealing, what is the radian? 1 radian is the ratio between the arc length and the radius. Arc length, that's unit of length. 1 inch or 1 centimeter on arc length divided by 1 inch or 1 centimeter radius. Centimeter cancels centimeter, or inch cancels inch. Radian is a unit, no unit. Okay? Radians is not a sparkle dimension, like length. So it doesn't bring your dimensions up or down. So d theta, in this case, does not give us a dimension like dx does. Dx goes from 3 to 5 meters. That's 2 meters there for dx to cover. Theta is in radians and does not have a unit to it. It has radians, but it's not a unit in terms of meters and centimeters and miles and inches. So you don't get the dimension from there. You only get the dimensions from here. This is your r, and r is length, right? R is the radius. So that is, I don't know, 5 inches, and then that's squared. This is from 0 to pi, 0 to 2 pi, 0 to 100 pi. So you're getting your pi from here, which travels through that one. So you get your pi, and you get your r squared, pi r squared. If you're interested about that coefficient half, it has to be there for the reason of the double. The period for sines, cosines, so is 2 pi. So there's doubling on the circle. Cut half. If you're interested, you can read it in the book. It's in a margin, actually. But this is the formula. This is your function. So if I ask you what is the area of those 4 petals of the flower, this is where sine 2 theta goes. You want the whole flower from 0 to 2 pi, and just crank the integral. So that's the first one we're going to do. I want to know the area of the flower from earlier. And please, next date, bring it up. Yeah.
I'll try. I get nervous on this.
It is going to be a great icebreaker because probably the date will have no clue what you're talking about. So,
And run screaming into the night.
nah.
Yes, they will run screaming
Nah.
into the night.
No, I always wonder, it's like, if I ever go out, it's like, so did you watch the game last night? First of all, I had no clue there was a game. All right. Second of all, if you kill him, like on a gunpoint, I can't pinpoint which team belonged to which sport. All right. So it's like that's another one. And yeah. No, those I know. But that's serious stuff.
Otherwise I can get you thrown out of the man club.
Bring it on.
So, oh,
Together, if you want.
you try to circle the right this time.
Oh yes, we were supposed to talk about this, the flower.
We're going to do one.
Yeah, sine 2 theta. Have fun.
Oh, no.
It's sine 2 theta, and it's going to be theta between 0 and 2 pi. You got this. Find the area. Find the area. It will give you the area of all 4 petals. Guys, just plug and pray. You know how to do trig integrals. I'm even going to leave now.
The integral of sine is negative. Wait, what do we have to do before we plug in?
Something before you plug it in. I don't know what, but something according to him. Don't look at me, I'm the dumbest kid in the smart class.
No, I think I'm the dumbest kid in the smart class.
I have been the
no
dumbest
idea
kid in
what
the
you
smart
said about
class
this
since
entire class.
1972. Actually, still be 73.
This entire class, my mind's a complete blank. Nothing. He said find the directions of sine. I said, what the hell is it?
We have to do something first. Power reduction formula. Oh yeah, like I got that memorized. Let me go find it. Power reduce.
It's just sine squared theta though.
That's what it is.
Sine squared of 2 theta. Yeah, so isn't sine
No, not
squared
power reducing.
just
That's sine 2 theta, not
cosine
sine squared theta.
of theta, of cosine 2 theta minus 1 over 2?
Well, wouldn't you reduce it first before squaring it up again? Wouldn't you use the half, the
That's what I'm talking about. Half angle isn't
the double
squared,
angle?
something like that. You just
Oh,
call it power
yeah, that's what I'm
reduction.
saying, so isn't
Oh, he said that doesn't work out the good?
But he
well,
said,
sine
or
squared
he
of
calls
2
it the
theta.
power reducing formula.
But it's actually this one here, right?
No, it's not that one. It's, yeah.
Right. So this is the.
Yeah, but-
So because it's sine squared of 2x, or 2 theta, it'll be 1 minus cosine 4 theta.
But, so you're putting it up in the formula before you're reducing it?
And this is
Right. You have,
theta, right?
it's not squared before.
I'm trying to figure
Oh, are you saying make it 2 sine theta,
When he
cosine theta?
said, I'm gonna integrate blah, 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 he said, you gotta do something else first.
Yeah,
What's the
I
something
wasn't
else?
worried about that.
Oh, you're northern Dakota.
Yeah.
I think I'm just gonna wait till he comes back and shows us because I haven't done this.
Well, if you want to look, I'm doing it.
I'll watch you.
No, wait. So you have.
And then we go like to do it.
But how does it become sine theta? But why do you get that though? Wait, 2 sine theta? 2 sine theta is equal to sine of
Sine 2 theta is equal to
Write it out. That's what we have to solve. It's sine of 2 theta. What is it? This?
Oh, it's right off the function.
Yeah, that's what I'm saying. Then don't you have to change it to the coordinates? So it's cosine of 2 theta minus 1 over 2. Is failure an option?
So the answer is obviously
5,
6.
253.
so 1080p. There are 4K. So I have two serious answers, which are pi over 2 and pi. Multiple people on pi over 2, and one person, as I heard, at pi. I'll give you another 6 seconds.
I'm probably gonna sound really stupid, but once you substitute your sine of 2 theta, and so it's sine squared 2 theta,
Yes.
you have to convert that to the trig identity. So
You must
cosine.
use power reduction. There's no other way to do it.
Yeah, the power reduction of sine squared is cosine
Yes.
squared minus 1 over 2.
1
Cosine 2 theta.
minus cosine, and it would be, in this case,
one-
4 theta, because it doubles the angle.
Yeah, so 1 minus cosine
4 theta over 2 gets kicked out as 1 over 4, and yeah.
Oh, okay, so I was on the right track before someone.
I'm sorry, did I mess you up?
No, I'm looking at you guys say
Yes.
I over 2.
I have 4 people that say pi over 2 so far. So I'm inclined to say pi over 2, but let me make all my mistakes and then we'll see.
All your mathematical mistakes.
Yes. So it's going to be 1/4 integral 0 to 2 pi 1 minus cosine 4 theta in parentheses d theta, which is equal to 1/4 open parenthesis theta minus sine 4 theta over 4. This is when you get your over 4. I would never. 0 to 2 pi. This is going to die in both cases because right at each pi or at 0, sine is always 0. So all it's left, it's 1/4 times 2 pi, which is pi over 2. I would say the answer is pi over 2. What is the area of a single petal? Divide by 4. Pi over 8. So each one of them is pi over 8. Just.
Wait, why did you said sine of 4 theta goes to 0 because
Sine of 8 pi is 0, and sine of 0 is 0.
okay.
Right? Sine is 0 at every pi. Sine n pi is 0 forever. Right? Sine n pi. So I don't care whether it's sine 2 pi, 4 pi, 8 pi, 5 pi, negative 5 pi. They're all zeros. And then sine of 0 is 0 as well. So it dies for both of those. Theta is the only one. It was theta when it's 0 dies as well. So the only one that stays is pi. Great.
So then it's 2 pi minus, how did you get from that one where you're crossing out the sign and putting the 0 at the top to the 1/4 2 pi? Is it
1/4, and then you plug in 2 pi for theta.
2 pi for just plain theta?
Yeah, and I didn't
There's
plug
nothing
0.
else to do because that's crossed out.
Exactly. There's
Okay.
nothing else to do.
Let me write that out so I know what that means. Step.
A cool question would be prove equation for the area of the circle.
Wait, what's the area of the circle?
Yep.
So from 0 to pi.
So what are you integrating? R.
Yeah.
So you're integrating R equals R.
Yeah.
Good.
Why?
Because the area of the circle is pi r squared.
Well, that's you should get that.
Yeah.
Now, this R represents any circle in a galaxy. Capital R is 1. It's a unit circle. If you're 3, then it's right. Radius is 3. So little r is the function R. Right? Capital R is a number that the radius would measure. So you will substitute that into your equation for the area of the, right in the integral. So you guys just compute.
Okay.
This one should literally take 18 seconds. Let's go. 13, 12, 11, 10, 9, 8.
Got it.
Mm-hmm.
Got it. The answer is 1/2 times the integral from 35 r squared.
You were gonna write down that the theta was between 0 to 2 pi, right?
What? I only have one, okay? This is my sugar to get me through this. What?
You're a theta.
All right, so the time expired. All right, we have 1/2, 0 to 2 pi because I want the entire circle, and I am plugging in r squared d theta, which is 1/2. This is capital R, so r squared theta from 0 to 2 pi, which is r squared times, 1/2 r squared times 2 pi. These guys cancel, minus 0, so pi r squared. Done. It is a very easy proof. Any time in life you run into someone who's questioning the validity of the area of the circle equation, there you go.
What if they
I'm
question
gonna
the
say, 'cause that happens in my too.
What if they question the validity of an integral?
Oh, you can prove that, you can show that as well. You know the rectangles thingy and then just Riemann. So yeah, you can do that. From Calc1. That's the beauty of mathematics. Yeah, sure.
So, just a quick question. Well, you used to worry about the representative rectangles, the x, dy, right?
Yes.
Now here, do we only have to worry about d theta, because there's no way to get the dr one, right?
Very good. It is the only way it can be done. It's d theta. That's true. However, there is a worry, a very scary worry with these integrals, and it will be apparent in Calc3. And that is area between two curves. You have to solve trigonometric equation every time to find the intersection points, which is the next problem. So as you are dealing with a single problem, I am able to find area of any portion of a circle. Just for fun, you can ask someone what's the formula for 60% of the circle or half a circle or so on, right? Area. You can find those by simply adjusting the theta. Because if I'm looking for the area of the circle, my angle 0 radians starts here. And if I only need a quarter of the circle, I will end up at pi over 2. And this area over here is 1/2 0 to pi over 2 r squared d theta. Now, it should be common sense that the answer eventually, when you compute everything, is going to be pi r squared over 4 because you calculated quarter of the area of the circle. But you can calculate, they're obviously all the same, but you can calculate area of that circle in any position because you're going to start with a lower limit. So if you want to compute this area, the third quadrant area, you will start at pi, and you would go to 3 pi over 2. You're going to get exactly the same value at the other end because the area is the same, right, anywhere. But you can start calculating these. You can calculate half of the petal for the flower, half of the flower, whatever, just by playing with those limits. But you have to be very careful with those limits because those limits can double up on your area, right? You don't want to go from 0 to 4 pi, right? So 0 to 2 pi should transverse the entire polar graph. And then you can get the smaller areas by using smaller values. Wow.
So like you said that the flower thing to do the integration. So
You need equations in the flower thing.
I don't know, you said that it is very important to integrate the function.
Yes, well, we integrate the function. In this case, function is very, very simple, just r. Nothing special, right? But the next question will be, what is the integral, area if I intersect two circles awkwardly, or flower in a circle, or cardioid in the circle, or any of the other shapes that we can draw using polar coordinates? How do I find area of those intersections? It is again going to be the game of top minus bottom. That doesn't change, just like in your 6.2. That part stays the same. But the scary part are those limits. And that's where you have to, because often you have to solve trig equations. And if you are not able to solve trig equations, then you can't get the limits, and obviously you're setting up the rest of the integral, well, tough luck, right? So, for instance, I'm going to just give an idea of what I'm talking about. So here, you see this? I ask you, what is the area of this, right? That's the question. So how do you approach this? Well, first of all, there are going to be these 2 points that live on these 2 lines. Now, I don't know now where those 2 lines are, but this is going to be your theta 1, and this is going to be your theta 2. I call them alpha and beta in the limits of the integral. Furthermore, as I draw the representative pizza slice, I have the far away minus close by looking from the origin. So the function that is far away is sine 2 theta, and a function that is close by, so this is r, right, sine theta, and this is r equals to some capital R. So now, when I want to set this one up, I have my 1/2, I have the integral alpha to beta, and I have the one that is far away, which is sine squared 2 theta minus capital R squared, everything d theta. So again, far, close, from the origin, okay? So origin is the center of the universe, and you measure from there. So far minus close, and you draw the representative pizza slice, it has to emerge from the origin and pierce through the area that you are calculating. Now, that representative pizza slice is going to start here and swipe that much, all right? So that's what the pizza slice is doing. So it's going to swipe this area here. Right? Starts at the point, 0, and stops. So now, how do you find alpha and beta? It's going to be sine 2 theta equals to r. The same way you did it for your area between two curves. You set two functions equal to each other, but this time you have trig equations to solve. How many questions do they have? How many answers do they have? Infinitely many, right? Okay, but we can actually at least get 0 to 2 pi, right? 0 to 2 pi is going to draw the circle, draw this, right? So at least on that much. But then you say, hold on. I know that I actually have 1, 2, 3, 4, 5, 6, 7, 8 intersections because I have my eyes to see that, right? So I just need to find the first two, and those are the ones. But then in all of my infinite wisdom, I said, well, no, I just actually don't want that. I want this one. Well, how do you get this one? Not that one. Subtract the other way, exactly. It's r minus sine. Perfect. But then I said, how about this one?
Which one you went to and one? Oh.
The whole thing over here.
The one actually looks like a piece of slate.
Yeah. It's still going to be the circle minus the sine, but now your r's changed, right? So these are the things that you actually don't get to learn from me. You have to sit down and keep pounding on different combinations because you are not used to this radial kind of thinking. You did not have a pita slice before as a representative rectangle, right? So now you have to first get used to the fact that that pita slice is the one that just does this, right? And it's going to go from the initial point and swipe all of the values. And then, as you can see, in this case, it goes like that. In this case, it's just going to be pinned here and then follow this piece. The flower is always going to be 0, so you're technically integrating only the circle, but in between these two, and you have to subtract the sides because it's going to fill it up a little bit. There are obviously different questions. Intersecting two circles, circle with a flower, flower with a cardioid, cardioid with a circle, cardioid with cardioid. You can get all of the different shapes. The question is how vicious you are to remember as many different formulas and shapes as you can. So setting these integrals literally depends on your ability to solve equations. So I'm just going to add here 4 alpha beta calculation. Set sine 2 theta equal to r. So say that I have sine 2 theta is equal to, right, sine 2 theta. Well, that means that its top radius is 1. So this stretches 1. This circle has to be smaller. The capital R has to be smaller than 1 so that this picture is possible. Right? If R is equal to 2, then that circle is going to be over here because this is how long 1 is because it's 1 over there. So, so this R could be a half, let's say. So in that case, you'll have sine 2 theta equals a half. Now, as it goes in mathematics, quite beautifully, is that if you actually set this sine 2 theta equals to 2, because someone who didn't think about anything just said, R is 2, right? Let's just have an easy number. Well, there's no solution because they don't intersect. The domain of sine is from -1 to 1. They can't be equal to 2. That equation would have no solution. All of mathematics has to fit all the time. So clearly that this circle must have a value smaller than 1 or between -1, right, and 1. So, but again, lengths can't be negative, so from 0 to 1 is all you're allowed in this particular case. Now I could have had over here a 4, which means that this would extend all the way to 4, in which case I could have capital R to be 2, because then you would have a 4 equals to 2, and then you bring 4 there, and you have your 1/2, and it's still easy to solve. Our values usually land, the answers for these to be pi over 6, pi over 3, pi over 4, 0, like 2 pi, and stuff like that. Generally. But yes, you can get pi over 12 and pi over 8, sure. That's not, right, excluded. But generally, you know, it lands. Because, again, this is a problem that you... I remember a few years back for one of my Calc2 projects, and that problem is lost to me. I can't find it anywhere. There was an amazing project problem with the sprinkler system. It was engineering design, 100% engineering problem, awesome. I know you might not be interested in agriculture and flowers and grass, but it's an awesome engineering problem where it used these kind of things to supply enough water, and obviously since it's going in, right, has to be integrated polar coordinates. It was an awesome problem, and no matter how hard I tried, I just can't find it where it was. I think I gave that problem 3 or 4 years ago. If I dig up the project, maybe I'll be able to copy it or something. But you get to integrate and use polar coordinates actually to do this. I mean, I have a ton of other stuff for polar coordinates. And as I said, guys, what you're going to do with this is you're going to build it up in Calc2. So r comma theta comma z, r comma theta comma phi. Right? So you're just going to build the same systems into 3D and then do more stuff on top of this. So know it. Yes?
You pretty much answered my question. I was going to ask if you can use this on 3D objects.
Oh, yeah.
I was thinking like if you can use it on the cup, is how you would like where you would put the
You need cylindrical coordinates for that cup, which is Calc2. So I did assign once that problem for a Calc2, the same cup for the project, but it just makes a joke out of it. You literally have nothing to do. It's 2 lines. This is truth of every next course summarizes previous stuff. It makes it much easier. So right now you have all of your areas summarized. So you don't actually have to know area of the triangle or trapezoid or anything else because you have integration. And all of those formulas you can just filter out 100%. And then you do the same thing for volumes and so on. So the more math you learn, a lot of that stuff that you had to memorize previously, it can just evaporate. This problem over here tells you you can forget that the area of the circle is pi r squared. Yeah, for convenience you are going to use that. But if you know this integral, you are solving that problem and all other polar problems. So you are focusing now on this rather than on that. And this is something that you evaporate. This is why as soon as you complete most of differential equations, you just evaporate almost every formula you ever learned in physics. There's no need for it. Or chemistry, for that matter. You just show up at that point because you can just get all the formulas by looking at them. So yeah, that's the part. Let's take a look and set up. I probably will not be solving these integrals. I'll just be setting them up. You should be able to integrate stuff in life by now. So here is an example of circle and cardioid intersecting. I did not talk about the cardioid. It's called the cardioid, right? Cardio, heart. It looks like a heart. And depending on the orientation, it might all right, so that's, I'm not drawing it properly and then it's, There we go. Because I need to draw a circle now. All right, so the question is, how much is this area? Guys, this is all still done on XY, right? But we are using circle is r equals to 1, and cardioid is 1 plus cosine theta. So at this point you say, okay, there is symmetry over here. Both of these functions are even. We should be able to exploit that. It's very dangerous in Calc3, but here should be fine. There is this intersection point right here, which we clearly see where it is. But we're still going to compute it because we can. Okay? So I'm going to set two equations equal to each other. 1 plus cosine theta is equal to 1, from where cosine theta is equal to 0. And that happens at theta pi over 2 and 3 pi over 2. And I'm just going to say common sense. Right? Look at the picture. I use your eyes. So representative pizza slice is going to start at pi over 2 and swipe to 3 pi over 2. Now this problem is a little bit scary for a few reasons, but let's take a look at. So that's a 2, that's a 1, it's -1, it's -1, +1. These are the measurements. And the origin, big fat dot right there. So for the circle, we start here. At 0, and we go this way to pi over 2, which is the intersection of the two. But look at the bottom part. If it goes this way, it's negative pi over 2, which is this one actually. And this is the part where you have to be extremely careful. Do you have to go from negative pi over 2 to pi over 2, or from pi over 2 to 3 pi over 2? Well, that depends on what you're computing. You have to know that this is 0. If you go from intersection to intersection, it's from negative pi over 2 going through 0 to pi over 2. And that's going to compute this part. But then you have this piece. That can be computed from pi over 2 to 3 pi over 2. One more time, I hope everyone is looking at this. This is where the 0 is, this is where the 0 angle is. Positive angles, negative angles. To compute this portion here, where circle is on the top, in charge, you have 0, starting at negative pi over 2, all the way up to pi over 2. And now, starting on this side, if we're going this way, for these two bumps, I start at 0, and I go down to, I start at pi over 2, and I go down to 3 pi over 2.
Just go from 0 to pi to multiply by 2.
Sounds good.
This is symmetric through it. So this motion times 2 will give us the picture. Yeah. I know, it makes sense. It's math, obviously, right?
When's the slice be going from one function to the other? And do that rotate? Does it not matter?
It does matter.
That
So we have split. That's a split. Okay. So you have to split this particular one into two different integrals because so this problem, that's the reason why I have this problem. They're tricky, guys. You have to understand that the representative pizza slice is going to change the function, right? So if you start here, you go up to this point, you follow the circle. You see this top? See how it's following the blue line? So the entire area over here is just given as the area of the circle. That's it. And then we need this one. But look, now it's following the black line. That's the cardioid. Nothing for the circle. So now, from pi over 2 to pi, is this little piece over here. So what is this? And as a student, this is how, I was amazing at these. Sequences of series, 0, okay? But this stuff, like 150 out of 3, all right? So, I'm serious. Look at this. I go integral 0 to pi over 2. This is how I used to think. I wasn't writing this, but this is how I was thinking. I need to work on the circle, which is the blue line, from 0 to pi over 2, and then to that I need to add the area from pi over 2 to pi for the cardioid. This is how my thinking was. And
It's like pseudocode.
What do you
just take that and
you will just break it apart. And then you will, yes, and then you will just, I'm not sure, I'm not following what do you mean by pseudocode.
In other words, a circle is representing, the word circle is representing a function of some sort, as is the word cardioid, representing a function of some sort.
Mm-hmm. Yes, well,
Sort of
those
like-
are these
yeah.
are, yeah, these. And so, yeah, I'm not looking, to set this up right away. I want to understand it first. So, symmetry, cut in half, throw this in the garbage, that's that, right? And then go, oh, this is just a circle here. And this field area is just a circle. Okay, I integrate that from where to where? From 0 to pi over 2, right? That's just a quarter of a circle. Cool. I store this in my head. And then I need this piece over here. So that's just going to be the black one, right? And then I just go down from pi over 2 to pi. Because 0, pi over 2, pi, 3 pi over 2, 2 pi. Right? So as you draw this, it goes 0 to pi over 2, pi, 3 pi over 2, 2 pi. What's up?
Is every
Doid?
symmetric to the axis?
Hell no. Depending on how these are oriented, you can flip it in any of the 4 positions.
Sometimes you can't rotate.
That's true. That's true. But it would just be another integral. It's not a big deal. Exactly. So all I need to do now is to put 1 squared here, d theta, and the function squared here, d theta, and then crank the numbers. Done in the book. Scarier problem. So this is different than the previous ones because you have to split into 2 integrals. The next one would be, what happens if I shade this? If I shade this piece? Minus the circle. Good. Cardioid squared equation minus the circle squared equation from negative pi over 2 to pi over 2 or 0 to pi over 2 double. This is how cool this stuff is. But you have to get used to the representative pizza slice, which is going to go far and close. Far minus close from the origin. So the previous problem is solved. If I'm now to use green and say, all right, let's shade this portion here, the green integral would be 2 times, come on, pen, 2 times 1/2 integral from 0 to pi over 2 car squared minus circle squared d theta. So in my head, as soon as I come up with what the proper distances, relationships are, the rest of it is plug and pray. Yes?
Wait, why would it be the cardioid minus the circle? I thought it was far minus closer.
Yes, and you start from the origin,
Oh,
and you go out.
No, I mixed up the things. I thought the black was the circle. Hold on.
Yeah, black is the cardioid and blue is the circle. Awesome. So, and I'll actually write underneath here again, far minus close, so we understand what's happening. Don't forget to square them, right? That's in the formula, d theta obviously at the end. So you can have a lot of fun with this. This is exactly the stuff, yeah. This is the integration problem for the test, for the final exam.
This exact problem.
So on the final exam, we are having a review tomorrow. Is that overtime?
Yes.
No one said anything. I'm just going to pat myself on the back on this one. No one said anything. It was that interesting. Just for the stream, for the records, all 250 students sat patiently as I went over time, 5 minutes and 51 seconds. Bye, stream, before they kill me.